The normal distribution has a few assumptions. It's bell-shaped, it's single-peaked, and symmetric. The mean, the median, and the mode are equal. Location is characterized by the mean, mu. Spread, or variability, is characterized by the standard deviation, sigma. As mu changes, the distribution shifts to the left or the right. As sigma changes, the shape of the distribution goes from less variable, which is more narrow, to more variable, which is wider. There are certain probabilities that arise from the normal distribution. If we start at the mean in the center and we go out one standard deviation above and below, this covers about 68% of the observations. If we go out to 2 standard deviations above and below the mean, this covers 95% of the observations. If we go out to 3 standard deviations above and below the mean, this covers 99.7% of the observations. That was a quick way to get to a few probabilities, but there is a formula and Excel formulas and probability tables to get probabilities associated with the normal distribution. There are 2 different formulas that Excel uses to calculate normal probabilities and values from the normal distribution. Let's do some examples. We know the total area under the curve is 1. We know the curve is symmetric. So this means that half is above and half is below the mean. So let's verify this using the Excel formula. Suppose entry-level positions at a particular firm are normally distributed with a mean of 44,000 and a standard deviation of 7,000. What proportion of salaries fall below 44,000? Now we know 44,000 is the mean, so if we use the Excel formula and the norm dist formula, we get a probability of 0.5. Well, we would expect half to be below. What proportion of salaries fall below 55,000? So now we're changing our value. 55,000 is slightly above the mean, so we would expect to see a probability higher than 50%. If we use the Excel formula, we get a probability of 94%. What proportion of salaries fall above 50,000? Here we use the complement rule, since we're looking for a greater than probability as opposed to the less than probability. So we use 1 minus that norm dist function. We get 0.196. The standard normal distribution is bell-shaped and single-peaked and symmetric. And the mean, the median, and the mode are still equal. This time they're all 0. And the standard deviation is 1. These 2 properties make it the standard normal distribution. You can convert any set of normally distributed measurements to a common scale by calculating the z-score. This process is called standardizing. To standardize, we use this z-score formula. You can do it by hand, you can do it in Excel. In either case, you compare your sample mean to the population mean and divide it by the standard deviation. The z-score tells how far from the mean the observation lies. The probabilities from the normal distribution are, they still hold for the standard normal distribution. There are formulas and Excel formulas and probability tables to calculate probabilities coming from the standard normal distribution. Let's do a few examples. Again, let's return to these entry-level positions. Let's standardize the mean. We know the mean is 44,000 and the standard deviation is 7,000. If we standardize 44,000, we get a z-score of 0, which we should get. What if we standardize 50,000, which is slightly above the mean? We get a z-score of 0.86. If we standardize 35,000, which is slightly below the mean, we get a z-score of negative 1.3, which tells us it's negative 1.3 standard deviations from the mean. What if we want to find probabilities? So what proportion of salaries falls below the mean of 44,000? Well, we would expect to get 50%, so we won't do that one again. But what about 50,000? Or a z-score of 0.86. If we plug this z-score into the standard normal distribution function, we get a probability of about 80%. If we plug in the 35,000, or a z-score of negative 1.3, we get a probability of 9.9%.